Okay, so the Super Bowl happened last night. Did anybody care very much who won? No? You do? How so? Really? Oh, well, we weren't like actually rooting for either team, but we just generally don't like Philadelphia, so we're kind of, yeah, yeah. Well, I mean that's our opinion. No, it's not that we don't like the team. We don't like Philadelphia, the city. It's vile. It's a cesspool. I don't know. That's fine. My son has one of his best friends is a kid who their family moved from Philadelphia, and I said the other day, "Oh, those people were the last good thing that happened out of Philly since the American Revolution." And it was, "Oh, I can't believe you said that." Anyway, but no, my wife used to work there. She did not enjoy it, so that's all. But like I said, it wasn't a strong preference. We weren't exactly dancing in the aisles when Kansas City won or anything, so whatever. Okay. Anyway, so yeah. So where we left off was talking about client server and end-tier architecture. And we're going to do a little quick talk about that to help us get into the right frame of mind for tight versus loose coupling. So I'm going to go into Paint. It is funny though. The only reason we watched it, we don't watch the Super Bowl, but this year we did because my son had a friend over. They were supposedly going to watch the Super Bowl, but all they ended up doing was playing like Roblox and Fortnite for 5 hours. So, but yeah, his friend was an Eagles fan, so there was some light tension from that. But yeah, all right. Anyway, it's cool though. Whatever. So this is your basic kind of setup. You have your database tier, you have your server tier, you have your client tier. Okay. And all of these different machines, okay, so first of all, let's draw this business block here. All right. And we're going to draw an interface. Okay, so when a client joins the system, when they somehow connect to it, they're going to connect to this interface here, right? And I've made this little box here, an interface, if you notice that. And once they go to the interface, right, they'll automatically get directed by the system to join some particular server machine, whichever one that may be. And that server machine itself connects to another interface in the back to any of these potential database machines. Okay, that's the basic idea with end tier. So remember, with client server, everything that a user is supposed to need, or a set of users is supposed to need as far as applications and data, is going to reside on that one machine, right? So if you want to switch to something else, you got to go to a different machine or reconfigure your connections manually somehow. With end tier, you go through the interface to this particular server. The system's going to send you there, and then anything this server needs to do goes through another interface to connect to any of these database machines, right? So for example, you log into Facebook, Facebook says, okay, you want to run some basic Facebook applications, we'll connect you to this server that has those applications right now. And to do things like construct your feed, they may have to connect to multiple database machines at any time, right? And switch back and forth easily between any of them. So end tier enables that. So number one, it's vastly more flexible, right? If users are switching between applications, it's very easy to have this interface connect them to a different machine. If the server needs to connect to a different batch of data, that's already built into the system. Okay. Other things that are nice about it, you can scale these tiers separately. So for example, suppose you are running many more applications or more demanding applications that you can't run so many copies on one machine as you used to. Well, you can multiply the number of server machines without having to add on any new database machines, right? You can scale out that server tier independently of what else is going on. Likewise, if your organization has a whole bunch more data, but you're running basically the same set of applications for the same set of users, you might need to scale out this database tier, add more machines there, but you don't need to add more server machines to manage them, right? With client server, you would need to add more machines. Okay, so again, end tier much more flexible, much more scalable. It's designed to experience, continuous growth and manage that, whereas client server, not so much. Okay, now for tight versus loose coupling, and we'll return back to end here to talk a little bit more about that. So tight versus loose coupling basically means how dependent the system components are on the structure of the other system components. So if you want just kind of a simple intuition about what a tightly coupled system means, imagine if you have some mechanical system full of gears, and those gears are super precise. Okay? If you have a set of super precise gears, that machine may work very well. It may last a very long time. It may run very smoothly. It may offer a high degree of performance in whatever metric you're measuring it with. But if any one of those gears changes to a slightly different size, the system isn't going to run anymore. You're kind of going to have to redesign the whole thing with a new set of gears. That's basically what tightly coupled means. Okay, it means that the system components, if they're put together in exactly the right way that they're supposed to, the system's hopefully going to work great. But if you change a little piece of the system, there may be many other changes that also have to happen to enable the system to keep functioning. Loosely coupled systems, on the other hand, is that there's not so much precision built into the system. For example, I'm going to do this. I'm going to switch back to computer languages, okay, which is something I can talk credibly about. Okay, so we'll talk about video games. All right, now when you go to the store to buy video games, there's going to be one aisle for PC games, there's going to be one aisle for Mac games, another for Xbox, another for PlayStation, and so on, right? Another for Nintendo. Reason is, different machines have different hardware configurations. And the code is tightly coupled, we might say optimized, for those configurations. Okay, so if you have a graphically demanding program, like any kind of first-person shooter, something like that, that's like high graphics quality, whatever, it's going to need to take full advantage of the system's capabilities in order to hit that magical 60 frames per second rate, something like that. Okay, so again, you're going to write specific code to run on a specific kind of machine. On the other hand, suppose you have some crappy low-end web app, like say Candy Crush, okay? Not very graphically demanding, or at least it shouldn't be, right? You could play some basic low-end version of that, which means you could run that on pretty much any browser or pretty much any hardware, okay? The difference is these kind of tightly coupled systems, they're going to be higher performance because you're specifying the graphics code for a particular hardware configuration. You can squeeze the most performance out of that hardware. With the second one, with the low-end web apps, you're just going to say, well, we're going to write some code, and we're going to have to somehow kind of translate it either through the browser or through some platform-independent language like Java or JavaScript, and we're going to make it run, but it's not going to be uniquely specified for each kind of machine. Okay, so that's the difference. Is you have languages like this is a bit out of the scope, C++ or assembly, that are for specific systems, or code like Java or JavaScript that will run on any machine via translation, right? So essentially, C++ and assembly, they look at what the actual hardware configuration is, and they say, oh, the graphics card memory starts at such and such memory address, and if I want to draw a picture, I change that specific memory location. With Java or JavaScript, there's some translation process built in where the code instruction goes to some translator that understands, like, oh, you want to draw a line? Okay, let me look up where that position is on that particular machine. Okay, so it'll do the job, but the problem with this kind of low end is that by definition, if you've written some code that's going to run on any machine, you're kind of going to run on the lowest common denominator, right? So your graphics are not generally going to be super cutting edge with this sort of model. Okay, you can do a lot more interesting stuff with the languages that are closer to the machines. Okay, so again, not to get super deep into the tech of all that, the key point, tight versus loose coupling, tightly coupled systems, all the components are designed to function really well with each other. And if those components are not there in the way they're supposed to be, it's not going to work well. Loosely coupled systems, you take a performance hit, but there's a lot more flexibility built into how the system can work. Okay, now, in terms of network systems, again, lightly coupled systems, components are combined with without that kind of mutual knowledge. So communication is going to happen through standard interfaces. So when we go back to this picture, this, if I wanted to, like, again, squeeze out maximum performance out of this system, I could specify somehow that, this user is always going to connect to this machine and a certain set of applications are always going to be available on that machine. And this machine is going to have permanent and persistent access to whatever data that I expect to have, right? You could make this system run faster by basically streamlining the process. But streamlining the process for everyone is going to be extremely difficult because you're going to have a lot of users that need access to a lot of different data, right? I mean, so think about client server. If you have, say, your accounting department, you basically know the documents they're going to need access to, and you could put them on one server probably. Something like Facebook, you have many different users with wildly divergent needs. Basically, you'd need a separate database machine for every user showing up to Facebook, right? Possibly more than one. It wouldn't really be feasible. Yes, you could make the system, run faster for a particular person, but that kind of setup is not really scalable. That's why instead of, say, having persistent connections to particular machines, you go through an interface, you dynamically assign, you're going to work on this server, and this server is going to dynamically pull data from wherever it needs through another interface. There's a little bit of delay, a little bit of looking around for stuff, but the system works a lot better in terms of cost than having separate hardware for every user, which at Facebook scale you just can't do. Okay, so overall, loosely coupled systems, they work through these kind of interfaces that all they do is they specify the format of the inputs and outputs, right? So a simple example there is Google. You go to Google, what is there? There's a text box, right? You enter some text into the box, send it to Google, Google sends you a web page of search results, right? So Google doesn't care what hardware you're using, doesn't care what operating system you're using, doesn't care what web browser you're using. All it knows, you got to Google, you put in some text, Google's going to send you back a web page full of search results, right? That's an example of a very loosely coupled system. Now, what makes that nice for Google is on the Google side of the system, they can change anything they want to, and the user's not going to see that, right? The user still knows, I just go to Google, I enter in some text. There may be some different mechanisms going on. Google's changed a lot of stuff in the last 25 years, but from the user perspective, it looks the same. Okay, that's kind of the magic of that kind of flexibility. So again, as long as the system conforms to that interface, it's going to make life a lot. It's going to work fine. And if we look at this kind of system here, this interface isn't really going to care what kind of server is being connected to, right? It could be any kind of server running any operating system, running any other applications. The interface just has to manage the connection. As long as the server can manage that connection, everything else is fine, right? Same thing for these database machines. As long as, whatever request is being processed from the server can be successfully processed at the database machines, it doesn't really matter what kind of machines these are. In a tightly coupled system, you'd probably have to specify a particular model of machine and work with that. In this kind of loosely coupled system, you don't have to. As long as any of these components meet the requirements and formatting of the interface, it'll be fine. It can work. Okay. Now, having said that, fast machines are going to work better than slow machines, but still. Now, what this means in practice is a loosely coupled system is going to be very easy to modify, right? So we talked about some things. You can scale out the different tiers. The fact that as far as within each tier, the machines are fairly modular because the user isn't worried. When you go to Facebook, you're not worried about connecting to a particular kind of server, right? You just need to go to a server that can run your applications and has access to the database. And as long as those conditions are met, it doesn't matter what kind of machine it is. That makes it easier for Facebook to swap out machines, to do upgrades. They don't really have to overhaul the whole system. They can just gradually bring in, newer machines as it becomes necessary. So loosely coupled systems, they're going to take a performance hit, but they are much, much easier to modify. And with a big system like Amazon, Facebook, Google, the fact that those systems are continuously growing means modification capabilities are pretty much necessary. You can't get around that. Okay. So, what the hell? I don't know what happened there. So again, advantages of n-tier architecture relative to client server. Number one, it is much easier to maintain, to upgrade, all of that. So the system components are modular, unlike client server, where a particular user is connecting to a particular machine and there needs to be compatibility built in that way. In n-tier, since everything goes through an interface, as long as both ends, the client and the server, can correctly connect with that interface, it doesn't really matter what the hardware is. There's a lot more flexibility built in. Likewise, isolation. Different parts of the system are isolated from others. So you can, for example, scale out the server tier without worrying about its effects on the database tier, or scale out the database tier without worrying about the effects on the server tier. Okay. Now, yeah, you may need to get like bigger interfaces or bigger switches with more ports, but that's about it. As far as security and reliability, again, n-tier is not automatically inherently a slam dunk better security than client server, but there are some advantages. One is that the application logic is internal to the business. So I'm going to poke through here. See all this behind the blue line, that's stuff that's internal to the business. And just like if you go to see a concert, right, you check in through security, they verify your ticket, they make sure you're not carrying any dangerous materials. And then once you've passed through that point, you're kind of free to wander around the system, right? So that's this kind of setup. In a client-server system, the user's already in the machine just kind of by virtue of showing up. So they have to be a little bit more cautious. But here, there's a login process, there's an interface, you get assigned to a particular machine. As far as client-server is concerned, if you have access to this machine and they can manage, your credentials there, they can manage your credentials if they check you into any other machine. It's going to be fine, right? Because that's built into it. So that's one. Because the application logic is internal to the business and data is only accessed through standard interfaces, it's going to be a little bit easier. Security can, what's the word I think? You don't have to worry so much about it, right? The interface does its job, then you can go to any of these places and they kind of don't really need to recheck your credentials a whole bunch. The second thing, easier system testing, right? So for example, that's more about reliability than security. With this kind of system, it's pretty easy to see what happens. Oh, I have a whole bunch of machines. If they start getting busy, I can bring some new machines online, right? And you can get some ideas about what the time delays are for bringing on new machines and how quickly demand changes. That's going to be a lot easier to manage. And the fact that you can scale those out separately, you can have machines available but not currently in use, it's going to be easier to do your testing for typical use cases. Also, the fact that in this kind of large-scale system, different servers are going to be running, each server is going to probably be running just one application. So, excuse me. So when you add more users to it, the load on the server is basically going to increase linearly, right? If everybody's doing video streaming, that's each user is going to be putting on a lot of work on the server, but you'll know how much work is going to be added for a typical new user. If you're doing client server, where all the users are using a different mix of applications, then you might have an easy case where they're all doing something undemanding like MS Word, or you might have something very demanding where suddenly every user decides to start using some high-intensity number crunching application, right? So it's harder to manage that sort of quality of service. For this, the big thing is just that each individual server is running a particular application, and so it's easier to predict how many users each server can handle. All right. And finally, scalability. So we talked about how the tiers can be scaled independently, but another thing, this kind of modular setup makes it easier to migrate things to the cloud, which businesses have been doing for 10, 15 years now. So, for example, suppose your business says, well, we want to run all the applications on our own premises, but we have more data than we really want to deal with. Well, some or all of that data they could put in the cloud. And then instead of accessing data stored on their own machines through an interface, they could access data stored in the cloud through an interface, right? So they can migrate just this part of the database system to the cloud. Or they could migrate part of it. They could say, you know what, we got a few machines that are really busy. We're going to keep them on premises for, optimal performance. But this other data, all of our cold data, we might store that in the cloud because there's a pretty good chance people are hardly ever going to ask for it. And if they do, we can deliver it a little slower. It's not a big deal. So you could split that database tier. Same thing if you just want to send all of this. If you say, you know what, it's costing too much. We don't want to manage our own database machines or our own server machines on our property. We're going to get that to a cloud service. Well, instead of this interface directing to hardware that you have on premises, you just have that interface direct to the cloud system. And then the cloud system manages all those same issues that you used to. All right, so yeah, in many cases, so a lot of the early cloud systems like Google, Facebook, Amazon, they grew very naturally out of this kind of N-tier architecture. For other businesses that were implementing N-tier, it was a useful stepping stone to the cloud. They said, well, cloud isn't ready for prime time yet, up until like 2010, 2011. But they saw, yeah, eventually it's probably going to happen. And when it does, we'll be a lot readier to do it because we've already built this kind of modularity into our systems. Okay. All right. Questions on any of that? Would you like to know more? I tried not to go into too many rabbit holes, but rabbit holes are inevitable. So big thing, tightly coupled versus loosely coupled, right? Tightly coupled means high performance, but hard to modify. Loosely coupled means you take a performance hit, but it's going to be a lot easier to modify. And in a lot of these modern large-scale systems, flexibility matters more than raw performance because you're always going to have to be expanding, right? We talked about how Facebook is adding basically like 1,000 hard disks a day just for the original copies of photos, not even talking replication or other data. So it's constantly growing. If you have a system that you're trying to optimize in some particular historical configuration, it's just not going to work well. Okay, cool? Good enough? Okay. All right, excuse me. So next thing, imagine if you're doing some transactions, right? So of course, customers aren't the only people that are buying stuff through Amazon, for example. There are all sorts of other groups involved in transactions, like credit card companies, warehousing operations, shipping. Maybe you have to send a message to an outside seller. Well, remember we talked with interfaces about how data inputs arrive in a standard format, output is sent out in a standard format. Well, in this kind of transaction system, one of the standard formats of sending data would simply be an invoice showing a list of all the things that you're buying and who's buying them and how much it costs, right? You bundle all that information together, and different operations would use different aspects of it. So the credit card company, they certainly need to know who the person is and how much the transaction is. For security concerns, right, they may need to look, excuse me, for fraud detection, they might need to look in there and see, what kind of items are being purchased, because jewelry is going to throw more of a red flag than, say, I don't know, T-shirts. Warehousing, they need to know what items are being sent where, right, so they can get them to the right truck. Shipping needs to have an idea of the size and the weight of the items, which they can extract, by knowing what the items are. Outside sellers, maybe the outside seller needs to know the invoice of what's being sold so they can update their systems, or they can send out some, call up UPS and ask them to print a shipping label or pick up the goods and deliver or whatever. So all these different users, to some extent, they're going to need this kind of invoice information. All right. Now, if you do place an order, suppose Amazon is going to use some kind of invoice object. So this kind of data structure is called an object. And Amazon would build an invoice object from the ordered items and then wrap some metadata around it. So remember, metadata is data about the data itself. So data about the invoice. So our example, Joe Snow, he orders a red hat, yellow shirt, blue pants, and a hardcover copy of Green Eggs and Ham to be delivered to 456 Igloo Circle. Okay? Now, of course, there are many ways you could write an invoice object, right? There's not just one way to do it. Many different possibilities. But let's say we take a simple human approach that's easy to understand, and we say, well, we're going to track the customer. Customer's Joe Snow, right? Because a lot of people are going to need to know who's buying this. Second thing, the address, right? So the address is going to 456 Igloo Circle, and let's say that that address is in US format. So that's metadata right there, right? It says this address is in US format, not say Swiss format. The item count. There's 4 items that Joe is buying, and that too is metadata. It says there's a list of 4 things. So the list of data is one thing, but somehow extracting from that, there are 1, 2, 3, 4 things being bought. That's data about the data. And last, the items themselves, right? The hat, which is red, the shirt, which is yellow, the pants, which are blue, and the book, which is Green Eggs and Ham, hardcover, okay? You somehow bundle all of that data into a standard format. Now, there's a couple different ways, couple prevailing formatting techniques. One of them is XML, which stands for Extended Markup Language. So, XML, if you've ever done anything with HTML, XML looks a lot like HTML. It has pointy brackets to be like tags for object attributes. We'll just give an example on the next slide. So XML, it's still out there. You can still find it. I'm sure there's still some businesses that rely heavily on it, but it is in decline. You know, you definitely have to work harder to find it than you do now. Reasons are, number one, it's relatively bulky. And by bulky, we mean for the amount of data that's actually in the object, it requires a lot of overhead data to format that data into a proper object. So that's what we mean by bulky. It also requires some kind of conversion or translation for online use. If you want, you have this list of things, but if you want to display it on a web page, it's not automatically in a format that's conducive to being displayed on web pages. So again, you have to run it through some kind of translation process to do that. Not that it can't be done, but it's a headache that nobody really needs. Number 3, arrays. So arrays are structures with numbered sequences of data. So for example, in this invoice, Joe's buying 4 things. And it would be really nice if somehow we could automatically refer to the first thing or the second thing or the third thing in that list, so that if somebody, say, clicked on it when it was displayed in a web page, we could instantly figure out, you know, where the link to it should be based on that set of information. But again, with XML, it doesn't have an inherent way to put in arrays, which means you're going to have to do that by hand too if you want to have that extra functionality within a web page. And last, often hard to read. So people do tend to think XML is a little hard to read. Maybe you're different, so I put your mileage may vary, but most people seem to say, yeah, this isn't the best. Okay, so here's an example of an XML object. So the first tag, very start where it says invoice inside the pointy brackets, that's the opening tag for the entire invoice. And on the very last line, you see pointy brackets, and again with /invoice indicating that's the tag saying, hey, this invoice is done. In between all that, you see some lists for the customer, for the address, for the list of items. Now, I'll direct your attention in particular to customer. So all that stuff there, customer, first name /first name, last name /last name /customer, all that kind of, that's the overhead that is necessary to manage this data so that the attributes, you know, can be located. So Joe and Snow together comprise 7 characters of data. Wrapped around that, you have approximately 70 characters of overhead, right? Between the customer tags, the first name, last name tags. So it's not super efficient. Right now, if the last name and first name were a lot bigger and the tags were smaller, like FN instead of first name, sure, you could do something like that. You could make it a little better, but still, it's not great. You know, if there's 7 characters, there's a whole lot of overhead. Now, we'll look at the next one. JSON, or JavaScript object notation, is a different object notation style, and it's based on JavaScript. Remember, JavaScript is the language for writing active code on web pages, right? Code that actually does stuff. So the nice thing about JSON is because it's in a JavaScript format, it can automatically be read as JavaScript by ordinary web browsers, which means you want to display this object content in a web page, you could just copy and paste it. You don't need to do any special formatting. It's already, JavaScript compliant. It is widely used as, it is the dominant object notation for this sort of purpose. There are some competitors, like Google was trying to come up with a rival to JSON, but the reality is this. It's a lot of work to convert all your data and to convert all your processes to do a different format. So even if Google's system is a little bit better, it would have to be a lot better and very clearly better for like a wide range of cases to convince a lot of businesses to switch over, right? Because switching over is a lot of work. There's a lot of things in the world, that kind of hang on through inertia. But JSON is still pretty good, right? I'm not saying it couldn't be improved on, but what I am saying is that Google's alternative, Google is big enough where it's worth it for them to optimize away some of these problems. But most businesses, it's just not worth the headache to switch over. It's a lot of time and work and error checking to, fix those problems. All right. Now, advantages of JSON versus XML. Number one, it's a lot more compact, which we'll see in a second. And because it's more compact, you don't need as much data storage, and data can get delivered faster. Why? Because there's just less data to send. Now, living in a world where a terabyte hard drive costs like $40, right? Data storage is not that big of an issue for most of these businesses, right? I mean, it's nice, but it's not a huge problem. But the delivery time, that's a bigger issue when you count, and especially because the cloud systems, they tend to charge by the byte. So if you're using, twice as much data in the cloud because you're sending a lot of data over their networks because it's not structured efficiently, those costs are going to add up a lot. And the other advantage versus XML, you don't need to do any conversion or other reprocessing for typical web page use. If you want to display this object as, a web page object in JavaScript, you just copy and paste the code and it'll work fine for that. Okay. So typical object format here in JSON. So number one, we have the customer, right? And you can see that the tags aren't repeated, right? Customer is the first one. Then there's first name, then there's last name. I mean, if you wanted to, you could wrap all this up as an invoice too. I just didn't do that here because, I don't know, things got a little weird. But I guess I could. And more likely, you would just give it a name invoice, which is fine. But you can see that because it doesn't have the closing tags, it just closes out the brackets. You're saving a lot of space there, right? So for example, in this case, customer, Joe, and Snow, you have same 7 characters of text, but about only 40 characters of overhead. So it's a lot better. All right. Anyway, so object description languages. If you have an interface that's going to expect data to arrive or be sent in a specific format, you need some standard format to put on that data. Objects are one way to do that, right? And 2 object languages, XML, which is bulky and not that widely used, and has some disadvantages as far as being shown on the internet, on web pages, has been pretty much made obsolete by JSON, which largely fixed those problems. All right. Would you like to know more? Okay, so now we've come to the part where I know everybody's excited about. We are going to do this thing. All right. I'll keep the recording on. That's fine. But we are going to have to switch over to a new recording. Once this is done, we're going to switch over and talk a little about Amazon Recommender System. I'm going to fire up Eclipse here. Okay, because Eclipse is where I run Java, and we're gonna see about this. Now remember the terms of the attendance lottery, right? You have to be physically present in class. So my apologies to people who are watching remotely, but in order to win this contest, right, you need to be physically present. So let's see, I got to change my run configuration on this because it's afternoon. So it's PM, not AM. All right. Bum, bum, bum. All right, so here we go. All right, should we do the check? If it's red, there's no money. If it's green, let's see. All right, let's see who we get. What the hell? It didn't crack. Oh. All right, well, it's still green. I'm not going to pull that away from you, but something went wrong with our, wasn't doing that the other day. last PM, first PM. Hold on. And see what happened there. List.length. Did I not fill out the list? 1 second. Oh, okay, yeah, okay. Hold on. I put the thing in the wrong batch. List is not a permanent. List equals combined, code equals 2, Arnix int list.length. So it thinks list length is, sorry. All right, we're just gonna try this then. Okay. I don't know why that happened. And now I'm troubled because I got to figure out this bug. So we're going to do this a different way. All right, because I know how many people there are. There are 153. So I'm going to pull the file from Blackboard here. So hold on, don't worry. So I'm just going to download the user info, and we're going to do a different way. I don't know what that problem is. I don't really have time to debug it. It was working fine last night. Okay, so here's the list, right? And everybody has a name. So we have from 1 to what? 152. So we are going to do this in just a second. We are going to equals int rand times 152 or 153. Let's 152. That's going to give us 1 to 152 plus 1. Okay. And when I hit return, we'll see what the number is. $50. 19. Bao Ying Chen, are you here today? Bao Ying Chen. Oh, very sad. Very sad. Does anyone know Mr. Chen or Ms. Chen? I'm not sure. No? That is very unfortunate. Oh, well, that's life. What? I mean, that's the deal. That's unfortunate. I was looking forward to giving away some money, but not so looking forward that I was just going to give it away for no reason. All right. But Wednesday's another day. Okay. So I'm going to stop that.